Okay, well, I put up this problem on doing impact testing using our impact tester. And hopefully you had some fun working on it a little bit. Two parts was to calculate the impact velocity of the instrumented missile. And then the other part was to sketch out a PVA, position velocity acceleration, of the missile as it contacts the test surface. So this is the instrumented missile from our impact tester. This is the shoe, or just the test material. And the way the machine is designed is that it will drop the missile from a height of 50 millimeters above the surface of the shoe, or whatever the test material is that we're testing. I've actually tested other things like chest protectors, rib protectors for football, other types of foam. You can put pretty much anything in there that fits and allows for a 50 millimeter drop height. So the first question was to calculate the impact velocity. What forces are acting on this missile? Well, when it's falling freely, it forced due to gravity, F sub g. And we know if we add up the forces acting on the object, we get ma, whoops. In this case, we've got a negative force, and we know that that will lead to an acceleration of negative 9.8 meters per second squared. Remember, this is the acceleration due to the force of gravity acting on the object. Okay? That's not gravity. That's the acceleration due to this force acting on the object. If we divide by the mass, we'll get g, and it's going to be a negative acceleration because the force is negative. Okay, so the first question was to calculate the velocity. I'm not going to do the math, but you should know your equations of constant acceleration. SI equals SF plus VIT plus 1/2 AT squared. That's a second order polynomial. You should recognize that. And the other main equation you need is VF squared equals VI squared plus 2A delta S. And good math problem solving skills, identify which equation you need by looking at the parameters that you know. And right now, we know the drop height, and we know the acceleration that the object's going to be, the missile is going to be undergoing during flight. So which equation do we use? We want to figure out initial velocity. Okay. Well, this equation has that position information known. That's good. It doesn't. We do not know VI, or well, we could do VI as being 0, and we have t. All right, but there's no velocity to solve for. So this equation we won't use because it does not have the parameter that we're interested in. We're trying to solve for the velocity at contact. This initial velocity would be the velocity upon dropping and releasing the missile, which would be 0, okay, if the machine's working properly. So we want to solve for initial velocity, and I should maybe call that contact. So just to distinguish it from this VI up here. Final velocity would be the velocity of the missile contacting the surface. VI would be 0, as I said, if the machine's working properly. 2, we know, A, negative 9.8 meters per second squared, and delta S, 50 millimeters. Now we have to convert that to meters, so that's easy. But now I know VI, I know A, and I know delta S. The only unknown is VF. So I'm going to solve for contact velocity, just doing my algebra and using 0 for VI as the square root of 2A delta S. Okay. That's now it's just plugging in numbers into a calculator, and you should get a velocity at about negative 1 meter per second. I saw one answer up there that came 0.999, whatever it was. Perfect. Okay, and that's the velocity at contact when we drop from 50 millimeters. This was chosen when they were coming up with this test standard because that's about the velocity of the foot while running and how fast it's going at contact. It's moving downwards at a rate of about negative 1 meter per second. All right, so that was part one. That wasn't too bad. And part two was to sketch out PVA of the missile, okay? So this is what we're gonna do now. Here's just a schematic or cartoon of what we have. The missile strikes the surface, compresses the surface, and rebounds. The velocity at contact is going to be -1 meter per second. And then there's going to be a velocity at takeoff because this missile is going to bounce back up in the air. Something to think about is the velocity at takeoff is most likely going to be less than the velocity at contact, meaning it's not going to bounce back up to 50 millimeters. There's going to be some, what we'll say is energy lost to the system, which is really a reduction in kinetic energy. And so we won't have the same velocity at takeoff because it won't bounce as high. And if we think about what the missile does, it hits the surface and it goes up and it slowly goes down, bounces a number of times and then eventually stops. Okay, so we want to sketch the PVA of this missile head. So I've got my model set up, contact, takeoff, time, same time axis, position, velocity, and acceleration. Notice I left room for acceleration to be positive or negative. Velocity can be positive or negative as well. And I did just leave position as being positive here. Now, the one thing I did do is I added in surface level here. So this would be the surface thickness. This is what you measure in your impact tester, is you measure how thick the shoe is before you actually do the testing, because the machine's going to lift the missile 50 millimeters above that surface. But I'm going to leave it like that because we're going to have some compression that I want to identify. So we got contact. So I'm expanding this time. Now, some of you looked at some times of contact, and this is probably really short, less than 0.2 seconds, maybe 0.1 second, all depending on how stiff this surface is. This is really a short period of time. I'm just zooming in on it. All right, so we can start anywhere here. Before contact and after the missile's been released, the acceleration is -9.8 meters per second squared. It's a projectile. The missile is a projectile. And after contact, when it rebounds, acceleration is also going to be -9.8 meters per second squared. It's a projectile going back up in the air. All right, I'll work this way, I guess. I'm going to leave it like that. And now I'm going to come over here and look at velocity. So we know acceleration is negative. That means the slope of the velocity versus time plot has to be negative. And we already solved in the first part that the initial velocity at contact is going to be negative. Now we calculated -1. So now I can draw in a slope. Oops. Oh boy, that was terrible. I don't have an eraser. Of -9.8 meters per second squared. Slope matches slope. Same thing over here. Slope with the velocity versus time plot is going to be negative. So I go up here. Where do I start drawing? Well, we know from the previous picture, the object, the missile is going to bounce back upwards. So the velocity is going to be upwards. Now, if this is 1, then this is 1. I'm going to do something less than 1 because I'm going to say it's not going to bounce as high afterwards. And now I can draw out a line that is parallel to that line. Slope equals -9.8 meters per second squared. Oh, now I got to connect those dots. Well, maybe before I do that, I go up and I think about position. What's going to happen to position? Well, on this side, on the left side of the dotted line, the object is a projectile. And likewise, over here. Now, I'm not indicating where it's hitting the ground the next time, but at least we're looking in this zoomed area. So we know that the shape of the position versus time plot will be a second order polynomial or parabola. I'll just draw that part. This is a parabola. Constantly increasing slope. Velocity is increasing at a constant rate. Acceleration is constant, negative 9.8 meters per second squared. Same thing over here, projectile. Now, where do I start this parabola? I could start it at the same surface height, meaning that the surface fully recoiled and returned to its initial position. Sometimes it doesn't. It stays a little compressed. And the impact tester will actually measure that. So I could start it like maybe it starts, the missile leaves the surface of the shoe actually below that level of the shoe. And this again is a parabola. Constantly changing slope, constantly constantly decreasing velocity. And velocity is changing at a constant rate, negative 9.8 meters per second every second. Slowing down, moving upwards, speeding up, moving downwards. Speeding up, moving downwards, slowing down, moving upwards. Yeah, and I'm not worried too much about where I'm going to get at the height, but it looks like it did a pretty good job here. That peak of that parabola will be right where velocity passes back through zero. I didn't do a good job over here though. That should, if that's passing through zero here, this should be the edge of the tip of the parabola. So bad. All right, so now what happens between here and here? Well, I'm just going to draw a sort of a uniform compression and recoil. I'm leaving a little space there just because it looks good. So now I have some compression here. And the impact tester will tell us the dwell time. It will tell us how long the materials compress for. That in essence is the contact time. It can also tell us how much compression there is as well. Okay, so now let's look at this, what's happening here. Slowing down, moving downwards, speeding up, moving upwards. Now, what's interesting is in this area right here, and a little bit in this area right here, we actually reach peak velocity in the negative direction shortly after contact. That is, the surface is not pushing up enough on the missile head to slow it down, and the missile is still speeding up while moving downwards. I didn't leave enough room here, but there's still a little bit of negative slope right after contact. So right here would be peak negative velocity right after contact. It looks okay on my paper. It doesn't look so good on the screen there. I'll stick it out. And then what happens? Well, we're going to go through this min here, which will be a 0, and I'm not doing a great job with some of the curvature here, but I'm not going to draw a straight line because I know acceleration is not going to be constant in this area. And then same thing on this side. We actually reach peak velocity right before the missile loses contact. So we actually slowed down. The shoe is not pushing up enough on the missile so that the missile is actually slowing down while moving upwards. It's the problem doing it in pieces here, but I'll try to smooth it out with the pen. All right. Speeding up, moving upwards, rebounding, slowing down, moving upwards right before takeoff. And then it takes off and slows down, moves upward. It's rebounding in the air. Yeah. Well, if I make the line thicker, it sort of hides some of my mistakes. So that's a good thing. Okay, so now let's go down to acceleration. Now maybe you can see why this happens is now that peak velocity is where we pass back through 0 here. Now I got to quickly get up through that 0. I find my peak acceleration is going to happen somewhere in this region. So I'm going to be like this. And then the acceleration starts to trickle back off down to here. The magnitude starts to go down. passing through 0 at this peak, and then off into the air right here. All right. If I look at this acceleration, this is a positive acceleration indicating in this region, slowing down, moving downwards. If I look at this acceleration here, this is speeding up, moving upwards. When we do shoe testing, we typically are interested in this peak right here. Now I've drawn this uniform. It may not actually always be uniform, depends on the shoe. Depends on how much rebound there is, and depends on how much compression there is as well. But this peak acceleration is what we typically would record in order to look at the impact energy absorbing characteristics of a shoe. Now, I don't have force here, but it's easy. Just multiply every data point on the acceleration plot by mass, and we get the force. And so I would just shift this up to 0, and now I have a force curve that goes along with this. Okay, so peak acceleration, we may be interested in the loading rate, how fast this acceleration is going up. If you remember, that derivative of acceleration versus time is called the jerk. We already determined this time here is the dwell time, how long the missile is in contact with the surface. And that's your PVA for impact testing. Pretty simple. All right, hope that's helpful. Thanks.